Let's say we have the surface code implementing quantum memory. We can protect quantum states. Where do we go from there to realize fault-tolerant quantum computation?
Yeah, so there have been a series of evolutions. In the very early days, it was all about puncturing the surface code, cutting holes in it, and then braiding those holes around each other. That is not done very much anymore. The focus has moved to what's called lattice surgery, where you have patches and those patches interact. So done right, you turn a quantum computation into a complex three-dimensional branching structure that happens to map your data in the right way. But the actual objects can look quite arcane, no longer really able to identify, where is my C0 gate? Where are the different gates that used to be in the quantum circuit? You end up strictly with a three-dimensional structure that just does all of the work in one go. And that is, in my mind, where the future lies for the field, finding more and more efficient ways to convert quantum circuits into three-dimensional structures that are very tight and compact and do the work of the circuit without actually looking gate by gate at anything like the original circuit.
What is required to build fully fault-tolerant qubits?
So
the minimal requirements?
Minimal requirements, you can get away with as little as 17 qubits. So the smaller surface code, distance 3, you have a 3x3 grid of data qubits. It's 9 data qubits. And then you have 8 measure qubits to check those 9. So 17 is the smallest you can do.
Mm-hmm.
And then it just grows quadratically as you allow the code the power to correct more and more errors. So yeah, those earliest demonstrations, those smallest demonstrations have been made. The question becomes, when is it better to use a code of that form to do logical gates? The answer is not yet. So by a certain metric, if you use enough qubits, it's already possible to do better than bare qubit memory using the surface code, but it is not yet possible to do a logic gate and do better than a physical gate. So we're going to need physical error rates that are lower so that we achieve significantly lower logical error rates, that it's actually worth using error correction. It's not worth it yet.
Yeah, I guess then the next question is having this fault-tolerant qubit, what can we do with it? I'll say, how do we scale up? So because we would like to have fault-tolerant quantum computing,
that's right,
interaction between those qubits.
I mean, if it's just 1 or 2 or 3 logical qubits, you're not going to do anything useful, obviously, because I can simulate 1 or 2 or 3 qubits precisely on a regular classical computer very, very cheaply.
So how about going to 100?
So you would need more of order of 100. And even 100, it is yet to be shown what you would do with only 100 logical qubits that would outperform a classical computer. So much more likely in my mind at the several hundred to 1,000 logical qubits is where you have enough power to have a chance. Quantum computers are very powerful. People are very clever when it comes to programming algorithms to do quantum mechanical things. So you need quite a big quantum computer before you have a chance to outperform a classical computer. And the search remains for computations that can be done as soon as possible that will create data that you couldn't get by other means, whether classically computationally or simply going to the lab and mixing things or building things. You always need to remember that the fair comparison of a quantum computer is not with any specific algorithm run on a classical computer. It's with anything done anyway, anyhow, right? And if the cheapest, best, fastest way of studying a system is just going and building it, then you have to compare with that. Is it cheaper to run a computation on a quantum computer, or is it cheaper to just go and build, mix, study the system physically, right? Ultimately, from a business point of view, if you can spend $1,000 on an experiment and get the answer, you're not going to spend $1 million on a quantum computer to get the answer, right? So I would argue our field is very much still looking for something where you could save someone money or deepen someone's understanding of a quantum system using a quantum computer. But there are promising indications. There's a paper from Google just recently on looking at the structure of molecules. But again, it should be stressed that those molecules can have their structure studied using NMR, which is certainly cheaper than running a quantum computer.
NMR could be also analog quantum computer.
Maybe, but very specifically, there are well-known experiments to determine the structure of these molecules that don't require classical or quantum computation and are the standard way it's currently done.
Just like to understand, so for surface codes, do I correctly understand that it's mostly about figuring out what errors happened to a logical qubit, to like the physical qubits which comprise the logical qubit?
Yeah, so any error correction code is about determining when and where errors happen to physical qubits. You don't necessarily need to think in terms of, is it part of a logical qubit? But the main thing you want to make sure is that collections of physical qubit errors don't corrupt your logical data. Right? In a block code, you won't necessarily be able to point at a qubit and say, you are part of this logical qubit. It might technically be part of many logical qubits. The main focus is, can I identify the errors well enough such that logical data is not corrupted? Even in the surface code, when you run a computation, the structure is more complicated than allows you to easily say this part of the computation is this logical qubit. It's a structure that supports computation. It consists of many physical qubits. You want to make sure errors are identified and corrected so that the data running through that computation is not corrupted. But yes, as with all error correction codes, the goal is to identify physical errors and fix them in software so that you get the right answer from your computation.
Do we fix them, or we just keep track of that the error
Just
happened?
track them. Yeah. There's in very few, not zero, in very few quantum systems does it make sense to fix them. Some systems it does make sense. A specific example of that is if you have a quantum system that has a bias, for example, measuring a 0 is frequently much more reliable than measuring a 1. And that means that there are physical systems, and it's been published, where it makes sense to go back and fix the data so that the probable measurement outcome is a 0 rather than a 1, because you get more reliable data that way, sometimes very much more reliable data that way. In a truly symmetric computer where there's no bias between, for example, measuring a 0, 1 and everything is symmetric, then no, you would do it all in software. But it should never be forgotten that the details matter, and there are certainly systems where it actually does make sense to go in and physically fix the errors.